Welcome to this talk on performance-specific technology lookup table-based design of a low-dropout voltage regulator. We have two speakers with us, Dr. Sakshi Arora and Dr. Manikandan. So the organization will be like this. So first we will have a talk of Dr. Sakshi Arora. Then we will take a 5 minutes break where we can ask for the Q&A. You can ask speakers whatever questions you have, or you can also get freshened up during those 5 minutes. And then we will have a session for Dr. Manikandan. And after that, we have refreshment, the tea and the sandwiches. So that's how the session will begin. So let me introduce our first speaker for today. So she is Dr. Sakshi Arora. She had completed her bachelor's in BITS Pilani. Then she worked in the ST Microelectronics. Then she went on to do her PhD at Stanford under Professor Bruce Woolley. Her topic was high frequency multiple output DC to DC converters for system on chip. Then she went on to work with Texas Instruments, Kilby Labs, and now she's currently working as an assistant professor at IIIT Bangalore. So let's have a small round of applause for our first speaker today, Dr. Sakshi Arora.
Thanks so much. Everyone, thanks for coming to the talk. We'll be discussing performance-specific technology lookup table-based design methodology for LDOs, essentially a methodology for you to think about and design analog circuits, which we've not been doing already using this methodology. But we've taken a stab at giving you a step-by-step process for designing LDO or low-dropout regulators. The talk, we have these sections for the talk. First, we talk about square law limitations. If you've been designing circuits using square law, then we talk about how it's limited and it will be more and more limited as we go forward with process advancements. Then we go for a quick overview of the process. What do you do? If I can't use square law, what do you do? That's the second one. Then an overview of low dropout voltage regulators to enable the use of this approach in low dropout regulators. And then we have kind of covered the design space for LDOs, going from wideband high PSRR, LDO, fast transient LDO, low quiescent current LDO. Essentially, after this talk, you should be enabled to design an LDO on your own with pretty much corner cases of the specifications. Professor Manikandan has worked in a detailed fashion to give you a step-by-step method for each LDO. So by the end of it, we hope that this is a helpful talk and doesn't end at LDOs. We can take it to hopefully any analog circuit. So that's our hope. So let me start with square law, which is something all of us passionately started learning when we started analog circuits, and most of us are married to it. I certainly was for the longest time. So to say that square law has limitations only takes a lot of, guts. But yeah, it is what it is. So what you are seeing is on this plot, x-axis is the overdrive voltage, which is minus 3T. Y-axis is the intrinsic gain, JMR of the device. Right? So the red plot that you see here is what the square law would predict. It's just inversely proportional to overdrive voltage. Unfortunately, that's not true for two reasons. When I reduce the overdrive voltage and go down the axis, and secondly, when the technology shifts. So imagine a scenario where I'm designing a differential amplifier or an OTA, any analog circuit. I start crunching numbers with square law. I feed the aspect ratio or W by L that comes out of my hand calculations. I put that all in. And then I run the simulations only to see, oh my God, this is way off. By way, I mean underlying way off. It will be like super off, especially when you are targeting lower and lower overdrive voltages or weaker inversion, as we call it. Right? This is strong inversion, but as I go lower in overdrive voltage, weaker inversion. And you will see soon when we discuss LDOs, we are mostly operating at weaker inversion or lesser overdrive voltage. So I don't have the liberty of designing in strong inversion, which means that this is a problem. Why? Of course, it's a problem because as a designer, you want to give time to something which has value. So if I'm doing hand calculations, they better match with my simulations. Also, the period of time realized that it doesn't end at us, right? If I am using some hand calculations and multiple fudge factors to design my circuit, I cannot give it to you or you to take it forward. I have to be physically present to tell you, hey, I crunched numbers here and crunched numbers there. So two problems. First is I myself am disappointed because it's increasing my design time. It's not matching its need. Second, it's not scale friendly. It's not automation friendly. It's not sharing friendly. All those things are concerned, right? So I hope you are together here that what you see in the blue plot here is what SPICE fits out for you. And the red one is square law. And as you see, the difference increases when you're going for lower overdrive voltages. And it's not less when you look at higher, stronger inversion also. For 130 nanometer. Now, these are three plots to emphasize and bring home the point that let go of square law with respect. So you are seeing three plots here. The first one is 180 nanometer, 130 nanometer, 45 nanometer. You deliberately shrunk the node as you go right towards the slide. So the red one is essentially the same because it's a function of POV. So it will be 1 over some lambda. So it's given idea 1 over VOB, which is 2 over VOB. So which is why you see it's just same regardless of the process. As you imagine, that's not the case, right? So when we simulate, we see that the difference between SPICE and square law is so high when you go to say 45 nanometer. And of course, 45 nanometer also, if you go to industry, it will like what we are talking about, and even further. So it's like married to something which is not working. So that's what I think square law is, and perhaps it's good to just let go of it. But having said that, what do we do? So what are my options? Okay, square law is not working. I just have that in my hand as a trained analog designer. What all can I do? A few things that come to mind is, okay, so it's mu and C of W by VOB square, whatever, the equation. So I can perhaps do a mu time or some fudge factor I can introduce to come closer. That's my first instinct, right? So I started with square law and look at the simulation result. Oh my God, there's a mismatch. The next step I do is, okay, maybe let me see what, if not square law, there is some model that's fitting. Then I realized, oh my God, that's even not working because it will be a function. They keep changing. If you change VOB, W, what all do I do? It's not going to fit. So what's the other thing that I can do? I'm not sure if you've done that, but in the pressure of assignments, sometimes we just do a parametric sweep and be like, hey, okay, sweep everything possible. And then whatever is the result, just submit it the next day, right? And unfortunately, things don't work like that because of two big disadvantages. First is you won't gain analytical insights. Right? And machine is not going to throw topological advancements for you. Right? Fundamental limits. The beauty of seeing the fundamental limit of your own when you do calculations and simulate instead of just doing a parametric sweep is different. So there's value to it. As a designer, strongly recommend not doing that in the time crunch. So there's first we understood their square law, then we graduated to okay, let me do some kind of beta type POV square or something. And how much do I crunch? Then I move ahead and I'm like, okay, let's do a parametric sweep. Then parametric sweep is a problem. Why? Because that is machine doing something. Okay, you can wrap some sophisticated ML algorithm or something, but do all that. But at least at the same time, notice the depth in the circuit design. So what do we do? The important thing is you have models for a reason. If I can characterize a device in a different way and characterize it properly to design in a more tied with process kind of thing. I'll walk you through it. But just think about your model, square law model was an abstraction, which we simplified a lot. Let me not simplify that much. And let's see what I can do by first sitting with the transistor. I love saying this a lot, that before designing any circuit, forget about anything. You get a new technology, you sit with the FETs or you sit with all the devices which are there, characterize them properly, and then start designing. It will save you a hell lot of time. It might look like a task in the beginning, but we'll walk you through what to do. Okay. So if I was using a square law, what would I do? I have some recent model of some model which is giving me square law approximation. I feed it into my hacking calculations. I have a certain set of specs. Do some hand calculations, feeling the circuit, spice, disappointment, look back, disappointment, look back, error keeps reducing. Do some kind of tweaking here and there. We call it spice mounting. I'm not sure what you would call it, but and then finally get to the results. So that's one way of doing it, which is not recommended, and it's getting harder. It will take a lot of time. So what else can we do? What if instead of square law abstraction, I'm doing a more intelligent kind of abstraction where I create lookup tables for certain figures of merit. Okay, so we challenge the figures of merit also. Instead of just override voltage, let's get more creative about that. So Spice will help you create lookup tables. This one-time generation is what I was talking about. Sit with the transistor first before jumping to a big circuit, analog or RF. So then you have the same thing. Hand calculation circuit Spice results, and Professor Manikandan, when he shows in the design, you will see that this whole process, how it looks like in action. So if you're interested to read more, there's a very good paper by Jespers, and there's a book by Professor Norman and Jespers, which is on systematic design of analog CMOS circuits using pre-configured lookup tables. I know all this is fancy, but I like the word systematic here the most. Because it might look tedious in the beginning, but systematic stuff gives you easier results and more in the end. Okay, so I mentioned to you that where are we? We are at a place where we say, hey, square law, no. Parametrics, we no, big no, big no. Okay, so let's be smart with characterizing the process. We are there. Okay, but what do we characterize for? Okay. So you would be like, yes, I know VOV is my, or overdrive voltage is something that we are used to seeing so often. The thing is, yes, I remember designing circuits the first time around, and there will always be what is the overdrive voltage and then design backwards. You have to set some overdrive voltage and design backwards. Problem is there are rarely circuits where you get to choose overdrive voltage and be like, okay, let me give 200 millivolt in circuit. It doesn't work like that, right? So you're sometimes feeding a current or bias current, or you don't bias effect with on chip with a certain voltage. So this idea that overdrive voltage is some older thing that we need to start with is coming from square law. So when you see the forms, so we let go of overdrive voltage with grace. Okay. So there are three figures of merit for this design methodology. The first is GM1ID. Once you start designing using this methodology, GM1ID would be like your new VOV. It will be so familiar to you. You'll be like, yeah, I'm using the GM1ID methodology. That's what the other name of this methodology is. Approximately, if you're using flavor, it's to VOV or overdrive voltage. GMRO, this is something that you'll be familiar with, or intrinsic gain. The third figure of merit is transit frequency. It's not a physical kind of a form, but it is representative of the speed of the circuit. Right? So for a fast circuit, I would like to have a very high F. Right? So these are the three figures of merit, and it's my responsibility today to tie everything to LDOs because that's the topic of the day and not necessarily just human ID. So what you're seeing relevance for LDO design, we'll walk you through LDOs also in a minute. But the relevance for each parameter, current efficiency of human ID, replaces VOV in traditional design method. So think of GM1ID as a proxy for VOV till you get used to using GM1ID a lot, right? So it's a proxy for VOV. Why? Because VOV is such an important metric because it gives you a sense of whether the transistor is in saturation, peak inversion. That's the beauty of overdrive. Now, once you start using GM1ID, you'll get that, oh, okay, if I have a very high GM1ID, which means I'm in weak version. If I have a low GM1ID, I'm in strong version. So we get used to it. That's why I say underline the word proxy, because very soon you'll be like, okay, GM1ID high means what? GM1ID low of what? Like what you have the sense of DOV, you will get the sense of GM1ID also. Right? So GMRO, I think all of you know, intrinsic gain of a device. For us, it will be very relevant because it will translate to the LDO specifications, which I'll walk you through in a second. FT, again, very important, as I said, speed of a circuit for us, it will translate to LDO transistors. So all these figures of merit stay unchanged for LDO paradigm. So if you go read the book by Professor Mohammed, these are the figures of merit. You can play around with it, and I will keep your mind open and be like, oh, this is a new figure of merit. But for now, I think all these are working for us. And I don't want to be, these are the ones that you want to use because overdrive voltage would have been like that at some point, right? So we keep our minds open and be like, okay, this is the state there. Okay. So once you start characterizing the technology, instead of the ID-VOV curve that you are used to seeing, this is how the plots would look. On x-axis is GM1ID. As I said, we are getting used to the fact that GM1ID is our new key form of figure of merit. Y-axis is GMRO, and we are sweeping with respect to length, like FET length. As you'd imagine, the longer the device channel length, the higher the efficiency. So this is the first kind of tech plot that you use when you are designing circuits or analog circuits. The second is ID by W. And the current density. How much current can I get for a circuit? ID by W. So that's the ID or the current field effect over rate. This will help you a lot to size the time because that's our goal actually. The next one is FT. So x-axis everywhere is GM1ID. And we'll walk you through this process so you get comfortable with using these step plots. But you'll be like, okay, how do I generate these step plots? In order to generate these step plots, we take a simple. This is step one of designing analog circuits. Instead of jumping into the, say, if you're designing a differential amplifier, starting with differential amplifier, if you're doing that, stop, go back, look at the FET, characterize it this way. So you sweep the VGS, sweep VDS over FET. It's largely width independent. All the forms that we showed you are largely width independent. So you characterize the FET and say performance metrics like GM, RO, CGG, ID. All these are going to tie to your figure of merit that we spoke about. So save these GM1ID, GMRO, ID by W, FT2. This will be so powerful to let you design a FET with confidence, and we call it first time right design. So if you do this well, you are saving yourself a lot of spicy iterations, right? So you generate this thing. And using this, now I'm going to share with you how do you design the FET conventional versus GM1ID. Now we are together slowly to design the LDO together. But this is the first step, this is the FET. So say we ask you to calculate the aspect ratio or W by L for a given ID VDS. So if this square law was valid, we typically choose overdrive voltage of 200 millivolts, say. Then you can use your square law and find out. All of us are together here, right? This is 1-1. So now, obviously, we've discussed that there will be error sources, there's mobility, there's threshold voltage, lambda, short channel effects, neighborhood, whatnot, which will create problems here. So what do we do? So now we are moving towards a different methodology. So we start with GM1ID of 10. So we are slowly walking the process. We are used to VOV 200 milliwatt, ballpark GM1ID of 10. But this relation is square law dependent. You just think about GM1ID of 10 is our first step, for example. Choose length is L min. Okay. So say, for example, if area is your constraint, which usually for power sets it will be, L is L min. Now what you can do is, I know GM1ID, I know L. We know the FET plots, ID by W versus GM1ID. Let me slowly walk you through the thing. GM1ID say 10. I go all the way up L min. I look what is my ID by W. Yes, we're all together. Now, once I have my ID by W, what is my width? Width is, I know the current ID over ID by W. That gives me the width of the FET. Already know the length of the FET. So I size the FET using, these are characterized from the FET itself. So what do you think the percentage error will be? The percentage error will be nil. Why? Because I kind of hacked the system to get the device characteristics upfront, and I'm now using the same device characteristics to get the device. So there's no way that will go wrong. I'll share with you how a little bit of source of error can come in and how to fix it. But for now, we're together, right? Let me take a step back and just quickly summarize in a 30 seconds or so where we are. So we started with square law, mu and CX W by LDO square, and we saw that it will not be able to predict IDBOV curve accurately. So what do? We characterize the FET for 3 figures of merit, human ID, ID by WFT. Okay. And if I'm giving you the ID, then what you can do is set some GM1 ID for minimum length. This is how you can size, but you did device characterization first. Together, right? You will get used to it because you'll see it multiple times too. Oh, now what if we have a GMRO, right? We're designing for a certain intrinsic gain. We still have ID, but we have GMRO also, which is intrinsic gain of the FET. Again, we start with the process, assume GM1 ID of that. Now, please don't think of it as like a something in stone. You can challenge everything we're saying. You have to think of it as a methodology. Okay? So GM1 ID of 10. So from GMRO versus GM1 ID. Remember, we did this as one of the tech plots. Okay. So we have GMRO, this is intrinsic gain. X-axis GM1 ID, GM1 ID of 10. Now I want a certain GMRO. So for a 10, I can go all the way up wherever the gate, say I wanted a gain of 100, I'll stop at say 729. Okay. So then we give one more time. I give you the gain, give you the GM1 ID, which is 10. I take GM1 ID, whichever gain I want, I can get the length. So I have the length now. What else do I need? I come to the sizing plot, which is ID by W. ID by W versus GM1 ID. I know GM1 ID again, 10. Length I know, I can go get ID by W, which will give me other ID by ID by W. Okay. So the idea is any form that you're trying to reach, like GMRO, FT, etc., get the text plot of that first. Once you have the text plot of that, if the length you know, you're done. If you don't know the length, get the length. Once you get the length, come to this plot. This is your, what do I say, square law of substitute. So once you know, instead of square law, erase it, come to ID by W versus GM1 ID, and you can get the weight as this. Okay. So if you're comfortable till now, that's great. If not, you will get comfortable by the end of the problem. Okay. So we have understood how to set size of FET. We'll take a little detour now because we have to use all this methodology for LDO. So we'll give a quick overview of LDOs, but not so quick that you don't understand. Try to go that you are with me. The term low dropout regulator is loaded. So first let's talk about regulator. Then we talk about dropout. So a voltage regulator's simple job is to keep the output voltage constant. Now constant quote unquote because they be spread. It's nothing is ideal, but that's the role of a voltage regulator. Now a low dropout voltage regulator means what is the ratio of input to output. E small between input and output. If I reduce the gap, that's called low dropout. Dropout is the difference between input and output voltage. The smaller the difference between input to output, the higher the conversion efficiency. Right? Because efficiency is nothing but output by input and distance, right? So the smaller I make it, the higher my efficiency will be. I'm of course neglecting the IQ, the quiescent current that defines things here. Right? So
what you are seeing on your screen is a very simple representation of a low dropout LED. Let me walk you through the thing. This one is a fast FET. It's a giant FET which is supporting the load current. What is the load current? This load current is whatever the regulator is supplying. So what the regulator is supposed to keep your supply constant. Yeah, come on. So an LDO is supposed to keep the supply of a certain circuit that is designed for constant. Right? That's my goal. I want to keep it constant, which means that this R and at the same time feed a certain current. So current is being drawn out of a load LDO. The role of this loop, control loop, is exactly that. To keep this node voltage at a certain value. I am assuming you know analog 101, but I'll still walk you through the LDO loop once so that you don't lose track. Quick refresher. Say I'm drawing a load current. Any load could be there. Yeah. Think of it as say maybe a power ampere. So there's a load being drawn here. When I draw load current, output voltage goes down. And output voltage goes down. This node voltage goes down. This node voltage goes up. So it's down, down, yeah, down, down. So this one has a higher VOB, so it's more than my. Okay. So that's the role of an LDO, or especially the control loop. So whatever you want to learn out of LDO, if you know your control loop basics, great. This is a great way to experiment or practice. So this is the dropout voltage, and this is your LDO. We'll open up the diagram in a second. Okay. So there are certain performance metrics apart from obviously dropout voltage, which the LDO is supposed to do. The summary of all this is whatever the aggressors be, supply, load, I don't know, temperature, whatnot, just keep the output voltage constant, but as little spread as possible. That's the goal of an LDO. So all the performance metrics are based on that thinking, right? Line regulation, it's a steady state metric, which means if my supply is changing gradually, what is the output voltage changing, right? So delta VR by delta VP. Why we are walking you through this is when you see Professor Manikandan walking you through the designs, you can relate to what he's talking about, right? So line regulation, load regulation. So my output voltage, output current changes, so the load current changes slowly, gradually, steady state. What is the change in output voltage? I really do not want those to be zero. You don't want output voltage to change at all. Power supply rejection ratio is a high frequency metric, which means that supply noise will be varying with the frequency. And then how do you respond with respect to changing supply across frequency range? Transient responses, this load may not be steady. It might be changing with respect to time, right? You might be pulling a lot of current and then the data I by data is lot fast. Change in currents might happen. The LDO is still supposed to hold the output. Okay, so that's transient response. And you need to settle soon also. So there is the gain bandwidth or the unity gain bandwidth of the loop will decide how fast you settle back. So in a nutshell, for an LDO, it's a very simple schematic that I've shown down. This higher the loop gain of an LDO, the higher of all the steady state metrics you can hold well. Because your loop gain is holding the output voltage to a certain value. So that's the nutshell of an LDO. I'm showing you a quick PSRR plot here. This is how it looks like. X-axis, of course, frequency. And both these designs, Professor Manikandan will share. Say a wideband high PSRR LDO would look like that. A fast transient response LDO or an LDO which is internally compensated. I'm going to talk you through the compensation in a minute. Can look something like that. And so the idea is DC PSRR, which is low frequency. And we also, for LDO, care about how PSRR or supply rejection changes with respect to frequency. Okay, so these are just a nutshell of performance metrics of an LDO. Okay, so where we were, we started with square law. We said square law is, let's throw it out. Then we said, okay, there is technology characterization and we can use to design a FET. Then we said that, okay, we understand LDO engineering. Now the next obvious step will be starting to design LDO using technology blocks, right? So we'll walk you a little bit through that also. This word, we are discussing two LDO technologies. Three LDO topologies, we will characterize them into two distinct. I'll share with you the compensation will decide which topology we are going to talk about. But wideband high PSR are externally compensated. So when you're designing LDOs, you will see that two categories are very predominant. Externally compensated, where if someone gives you a giant capacitor, so you can take it off chip, put a big capacitor here. That's the first category. The second category could be completely on chip. So we don't have any liberty to put any capacitor off chip. That's the other category. We'll discuss that. So these are the two primary things that we'll discuss. Now this slide I want to, I think, spend a little bit time here. Now you saw, let me walk you through what you're seeing here. The same OTA that you saw here in this one, we are opening it. So let's walk gradually. There was a MOSFET and there was this OTA. We're opening, this is the differential amplifier that you saw as a symbol. And this M8 is the MOSFET. Okay. The loop is still active, right? All together. We're all together here. So now what we are going to do is to use the technology plots to design LDO. There's a very important thing about LDOs that we have to analyze as a step one, which is the frequency compensation or the stability analysis. If you've done the diffamp stability or you've done OTA stability analysis, you would, the only nuance that comes here is the variation of rate frequencies poles here with respect to load current. Okay, let me say that again because now I'll walk you through it. If I was designing an OTA, there was no load being drawn from an LDO. The specific thing about LDO is I'm drawing a certain load, right? So when I'm drawing the load, circuit parameters would change, right? Like GM would change, agency gain would change. So all the stability analysis, the pole zero analysis that you do, will keep moving with respect to load current. And I need to know that to establish, if it is monotonic in nature, to establish the worst case in order to design a workflow for it. So what we are going to do is, we are taking this circuit, we are taking the rate frequencies, and we are walking you through how they change with respect to load. And the purpose for that is establishing a design flow for worst case analysis for LDO. Okay, together. So let's look at the LDO one more time. So I assume we all have seen the what a pole frequency is. This node is a pole because it will take time to charge, right? In that sense, that's what we have learned. So in this circuit, this is a pole. We call it the output pole. Another pole, any node that takes time to charge. Another pole, output of the diffamp. This will also take time to charge. Another pole, the mirror pole. The idea for this one is it's a 1/GM impedance. So you would think that this is a high frequency pole. Right? So once I understand this, I can in my mind think that LDO will be having two poles. Like let me say two dominant poles. Output pole, input pole, or internal pole, external pole. So internally compensated, externally compensated in two cases, two broad cases that we got. So the first one is externally compensated, which is the case where say I have off-chip cap available to me. So I can put a giant cap at the output, make it dominant. Right? So let's come to this plot. This one, so now we're going to walk you through how they change with respect to load. So this is the pole at the output. The equation is written here, or the expression is written here. The expression will be impedance written here times the capacitance. So 1/ROX. Its dependence is proportional to IEEE. So intuitively, what you would see is when you sweep the load current, the output pole is going to go higher in frequency. Okay, so I increase the load and I see that the second pole will go higher in frequency. The unity gain bandwidth, the expression is here, but the unity gain bandwidth will also go higher in frequency. With load currents, it will go higher in frequency. So think about a scenario where I am drawing more and more load current. Monotonically, the dominant pole or the output pole will move out, the unity gain bandwidth moves out, and the pole here or P1 is not changing with respect to load, for example. In our case, that's the case. Okay? So if that happens, the worst case is what? The worst case is when the unity gain bandwidth is closest to this case, right? So if it's closer to the non-dominant pole, that's my worst case. Okay? So I'll give you a quick overview again. My dominant pole moves out as I increase the load current. The unity gain bandwidth goes out as I increase the load current. Say the second pole is steady, which means as I increase load current, my phase margin is going to go down. So all of us are together for an externally compensated LDO. As your load current goes up, the phase margin goes bad, which means that becomes your worst case. It's important to know the worst case to tie it back to all the technology plot stuff that we were doing and establish about. Okay. So the next case that we'll do is internally compensated. Yeah.
So can you please explain how is that dominant pole proportional to load?
So the output pole is what? R weight over CL because CC, this is non-dominant. This is non-dominant. It's not coming into picture as well. So R weight over CL. R weight is the expression output impedance is inversely proportional to load current, right? So the whole pole becomes proportional to load, right? Output impedance of FET. Yes.
1 by lambda.
1 by lambda. Okay. All good? Okay. Sounds good. So after having said this, let's go for the other case. Now we're calling it internally, externally, but you think of it as I have off-chip gap from the spec perspective. I have off-chip gap or someone is not giving me off-chip gap and asking me to fully detect the LDO. Okay, so this is that case where it's all integrated. Or maybe a very small gap is available. Okay. In that case, this pole becomes a dominant pole. And this case is something you would have seen in OTAs, etc. These are very Miller multiplication here. This is something I think we all are comfortable with. So the first pole or in this case, so think about this one as the dominant pole becoming this one becoming the non-dominant. Okay, the dominant pole, the capacitance is getting multiplied by the intrinsic gain of M2. So when you look at the expression for omega P1, here it is RO diff A pass, which is GM pass, RO pass inbuilt here, and CCCGD. Why the CCCGD got multiplied by the M8 way, and then so the proportionality becomes square root of I root. So this pole is again going to move out as I increase load current. However, the unity gain bandwidth stays as is because the gain is also scaling. The loop gain is also scaling. Intrinsic in internally compensated LDO, the unity gain bandwidth does not move ideally. Okay. But the external pole or this pole is still moving. So in this case, as I increase the load currents, it's going up. So does it become a good case or a bad case? Okay. Heavy load, yeah, heavy load now becomes a good case because I'm moving out from the given value. In a nutshell, what's happening is if I have an externally compensated LDO, the external pole is the dominant pole. So when it moves out, it gives me worse case. In this case, it's a non-dominant pole. So if it moves out, it gives me a good case. Okay, so we're together here. Which one is the worst case? Here it becomes the right. Okay, so this is the third case, which is a very low IQ case. Very low IQ case as a suppose I have an application like an IoT, etc., where I have very low current, quiescent current here. If I have very low quiescent current, what happens to the GM of this well? The GM will go. So imagine this case, if this one is GM over what? We said that the impedance at that node is 1 over GM, right? So the pole is proportional to GM. If I keep putting the current down and down and down, the GM goes low and low and low, which means this pole starts coming in. And this becomes the non-dominant. So this is the third pole. Dominant pole stays as is, non-dominant pole becomes the middle pole, and this one becomes the third pole. The important part here is that in this case, in this scenario, you're getting a very high phase margin or a 90-degree phase margin because your quiescent current is really, really low. Okay. So the idea behind this whole topology is two things. IQ goes down, this pole becomes this non-dominant pole, but also the RO, the output resistance of this diffam will also become very, very high, which will put the gain very high, the dominant pole very low. So that is the scenario, case 3. So we have understood the tech plots are necessary. We've understood the LDO stability is important for establishing the step by step, and you will see how it is coming into play. But the important part is we saw that there is a VDS that was there in the FET. The problem is that if I start sweeping VDS to a large value, like small steps if I do, then I can create a giant lookup table library. And it is hard for a designer to look and design for one tech plot. So this tech plot was for one VDS. Imagine for every FET, I do multiple sweeps for VDS. So the same FET that you were seeing in this one. Here, you remember, we were sweeping VDS. Now, when you start designing an LDO, your VDS, you would want to be like, oh, maybe 335 millivolt kind of a thing. And you're like, okay, let me sweep VDS to a large, like very, very small steps. The problem with that is a designer starts using insights because there are multiple tech plots generated for each VDS. So for LDO, what you can do before I hand over to Professor Manikandan, I'll take two important points. The first one is you can generate sub-tech plots. Because tech plots were generated for a certain VDS. Now, what you can do is for an LDO, you already know that MOS will see maybe 300 to 500 million. This one is so when you look at a topology, you can characterize, hey, this will not go above this much VDS. Let me create that subset of technology plots so that I don't have to look up through the whole range or automate the process so that I gain insights. Okay, so that's the idea of sub-tech plots. Also, for example, the pass FET, the giant FET that we were talking about, which should draw a lot of load current. Size is an important thing. So we keep length medium. So you don't have to sweep length for characterizing that. Just create for one length and then you can decide it. The idea why we are sharing this is that when you go out there and design it, you design for a certain VDS and you start seeing errors when you start designing. And that error is mostly because you fixed your VDS. Or you have to rely on the machine to look up the value for you. So in order to keep the insights with the designer, we recommend that we generate subset of the tech plots for an LDO. We shared with you what you could do, for example, pass FET. This to minimum length. You know, minimum length is what it's going to be. So why generate all tech plots? We know the dropout voltage, so we know VDS. Same way for CMOS load, I kind of see that let me generate a bound of length. And I know that certain, once you design for a DC operating point, you know, this is the range for VDSs. So just generate for those many VDSs. This part is mostly when you start designing and seeing what it's called, you can put it as an appendix. It's not something I think will break the flow. And the last thing that I want to share before I give is why did we discuss stability analysis for a technology flow? The idea is, say I'm designing our FET using tech plots. I walked you through the process, right? You know your ID by W, you current, which FET is on ID, so you know the width of this FET. But not just the width, you know the GMRO of the FET, you know the ST of the FET, everything because you have characterized that. Right? So now if I'm on this axis, so I'm giving you an intuition before you start plotting for it. You know that for this one, where it is internally compensating, this is your second point.
I'm designing for a 45-degree phase margin worst case, which means I'm designing for light load. And I know the light load parameters from my technology plans. As soon as I know my light load parameters, I can work all the way back. At least put my omega unity gain bandwidth right on top of it to get 45-degree phase margin. Right. I'm giving you a sample flow so that when you look at Professor Manikandan's work, it's like a transition is okay. Okay. So quickly again, I know I've sized M8 or the power FET. So that gives me all insights about the second port. As soon as I get that, I can fall backwards through the flow, get the unity gain bandwidth to the light load for 45-degree phase margin, and then step by step design the differential amplifier. And that's the work that Professor Manikandan will share with you. How do you marry the flow and the plots to design? Okay. Yeah, that's it from my side. If you have questions, I listen to it. And then we transition into giving you tangible examples. Yeah, these are the cases that I share. It's a lot of information in 1 hour. So if you have questions, please.
I request all the audience members, if you have questions, please raise your hand. I'll pass the mic down to you. Questions from the audience?
Okay. Good evening. Thank you for this wonderful talk. For the technology class, how do you gain intuition and what do you need to do to gain intuition about this technology class? So while now we have been taught how to gain intuition after a period of time. Here, how do we get that?
Yeah, I think that's a very good question. To gain intuition first, I'll tell you the steps, but I'm not sure if that answers the question. The steps I would do is not sweep everything blindly and get into the domain of parameters. So I would just say, for example, if I have to use technology plots for one FET, the same tech, yeah. Say, for example, I have to design one, I want to give me this. Yeah. So here the intuition was what? The intuition was if I increase the width, I get the current or the overdrive voltage is a knob. I think the word intuition I will translate to the word knobs and then the word knobs to technology blocks or square. In order for us to understand knobs, it takes time. So overdrive voltage takes time for us to build that, hey, the lesser the overdrive voltage, the lesser the current. Higher the overdrive voltage, higher the current. Or gain would become higher if I have higher length. It stays the same. Because now you are just having GMRO versus GM1ID. So the only shift you need is override voltage to GM1ID. That's the biggest shift. Once that happens, the framework stays the same. Because instead of GM1ID, instead of override voltage, my knob becomes GM1ID. So it's all the same, but instead of an equation, I would say it's better because you're looking at the plot, you're looking at the trends instead of just an equation. So to give you an example, this is a classic thing which I think, yeah. So when I'm looking at the math, I would be like, oh, given ID is 10, but this is ID by W is this value. But gradually over the period of time, you will realize that, hey, a lower length is a higher FG. A GM1 ID of 10 translates to 200 millivolt, but 200 millivolt will go away. GM1 ID of 10 will stay. So you start building intuition on GM1. I think it takes time, but the intuition knob just shifts in your head. And you start talking in GM1 ID terms instead of overdrive voltage with respect to the period of it. Like when we talk about circuit now, I just think of, oh yeah, this is higher GM1 ID, this is lower GM1 ID. So for example, give you an example, both of us are thinking about very low IQ LDO. So at least in my head, gotten rid of overdrive. And I'm thinking, let me track more and more GM1 ID, more and more GM1 ID. Then I will translate the facts into vehicle volume. Then get very low IQ. So the intuition is time. I would not say, but I would say counter intuition would be when you generate multiple tech plots and let the code run and find.
That is a red flag that we lose in the insurance.
One further. There was a Hashim Umran, you are familiar, we came across, he has brought out this tool called TDT, Analog Design Toolbox, where he has brought out the entire code into a GUI interface, where you feed the same and you get these parameters. So he's from University of Cairo. So when he brings that out, I hope you have seen that, because all this is right now a GUI interface, which is plug and play. So the need to do this is kind of lesser. So if you have context, everything, the technology plots that you're talking about, lookup tables, is already built all of it for certain nodes.
Yeah.
So if you feed the technology file that you get from the foundry,
That's a wonderful thing to do, because for us, this whole first part is just a mechanism to lead to LDO methodology. If I have a tool that someone gives me all this business or a GUI, for me it's like I'll use the LDO methodology. Then the focus is using this for LDO methodology. So it's for us, it's a very good thing, and we use it for LDO, and I would just grab it based on this. Because the idea is whatever it is, just give me a sneak peek into the process and don't create abstraction for me to generate an concept. If it's a GUI, give it to me and use it for something else.
Any more questions? Anyone? Actually, I actually tried to design some circuit, but I never speak the VDS because it is tough. So I'm just thinking that whether is it if we are able to control the VDS beforehand for designing circuits, because if VDS is high, then our GDS won't affect much.
Yes.
But for like suppose I'm designing a telescopic cascade amplifier with low supply.
Yes.
VDS is very good.
Yes.
Even if there is a reduction in VDS,
Yes.
the gain will vary.
Yes. Yes.
So is it possible? I'm just asking.
Yeah, that's actually a great question. Let me rephrase the question and go reflect it back to you. I don't think I have an answer for it, but I can just take a stab at what you're saying. So what you're saying is many analog circuits. Say I generate technology using low VDS. That is not going to be the VDS that I'm going to see. So that's where the biggest source of error lies, and that's what we saw also. The second step is let me generate for multiple. So there's a trade-off here. The trade-off is if I'm generating for multiple VDSs, then I lose insights. Then perhaps your GUI will help. But okay. So these are the two big trade-offs. That's why I started using these subset tech plots idea, which is again topology conscious. Right? Because you don't lose complete insight. So like for example, when I was doing this LDO for the class, I did not have access to given sample. This is just so that time I was like, okay, how do I figure this out? Then I realized this is very dumb for me to think that I should generate all tech plots when I'm very aware of what I'm doing. So this is a very, if you read Professor Mohan book also, he emphasizes that think of LUTs or lookup tables as just your tool. Think of your circuit block first, which is a job of a designer. As a designer, if I'm like, okay, I have tech plots now, I can generate LDO, that's not LDO first, understand it first. In our case, also think of the load varying the pole frequencies. If we would have been like, oh, let me sweep the load, let me sweep, that doesn't matter. That doesn't help you. Same way, if you're designing a telescope, you can create a bound on it. And maybe for our, I can just talk about our case. We're very sure about the range of VDSs that we will supply. When you start seeing it, it will still be error, but you will get to a very good ballpark number, way better than square. So I remember the errors that we saw was sub 10%, which is huge. But for a designer, first go, sub 10% is good compared to square law in 45%. So I would, in long story short, I would just say that instead of thinking tech plots as revolutionizing your circuit, think circuit first. That's the primary job. And then you set tech plots as you do. instead of vice versa.
It was can you pin down the BDS of each MOSFET before?
No, that's why we said how we cannot. We will just have a range. You just create a subtech plots. That's all that we know. But if you come up with something new to break this problem, please share it. For now, how we solved it was subtech plots. If you have more neat ideas, it plus. That's your source of error, and that will very well identified.
Okay, so any more questions? The offline audience, we have a couple of questions from the online audience. I will request the online audience to share more of their doubts and queries to make this interactive. I'll take maybe one more question from the offline audience if anyone has. Any questions from the audience here? Okay, so I see no hands. I'll move on to the online questions. So one of the questions is something that all of the students may be willing to listen to. So is there any free VLSI software that helps us do layout and LVS? Any open source, anything or something, if you know?
I just know of Skywater, but apart from that,
Yes, sir. There's LT Spice you can use. There is LD Spice which is coming across. OpenLane has got its own layouts. K layouts are available. Magic is available. Most of them have a Windows interface, or you can use an Ubuntu or Linux interface. Can you get it at tapeout quality? The last 2 years, the answer is tending towards yes. People are doing lots of layouts in open source tools. So Noah himself is leading it. I think now he's doing it at Florida, Hawaii. So he's leading it there. There is multiple people doing it from the University of Michigan also. In India, we have at IIT Jammu, there's a faculty who's doing it. There's one more. I myself have been doing a couple of them the last couple of years. So there are a lot of things, and you should definitely explore.
Thank you. So that was a quite comprehensive answer. So yeah, next question that we have is, can we use these tech plots for any design other than LDO?
yeah, why not? Yes, yes. The answer is yes. And when we were designing for LDOs, we realized that we were discovering more and more things depending on performance specific thing. So by all means, yes, please try. There are documented things for many, like OT you have, LNA you have, but that also is a very limited design space. When you go deeper into it, you will find more and more ways to develop. Think of this as very soon it will be just like Professor was saying, you have a GUI. So technology is not a this thing, it will not be a blocker. The blocker is you come up with how to use these tech plots for your specific design.
Thank you, ma'am. Then we have another question. Ma'am, can we use comparators as error multiplier? Error amplifier with inbuilt VREF in LDO architecture?
I've seen a paper, but I have to get back to you on that. Yeah.
So Prajwal, you can just
Yeah, please send it.
Send a mail or a message to ma'am, and she'll be happy to reply to it. So I see no questions in the online chat box as well. So anyone from the online or offline has any more questions, then I'll wait for another couple of seconds maybe. And meanwhile, I'll request all the offline audience to give a round of applause for ma'am. Yes. Despite the rain, all of you have talked about, that's the first thing that we all are grateful for. And the speakers are giving such nice talk, and it feels really good to have such an audience which is interactive. So thank you, ma'am, very much. And thank you. So we will have a small break of another 5 minutes. It's not the refreshment break, you have to still wait for the second half to finish. It is just for you to go out, maybe jog those muscles and get the blood running, and go use the restroom maybe. And yeah, we'll be back in another 5 minutes. So same to the online audience. Please stay tuned. We have the next part of the tutorial coming up. And thank you.
Okay, so let me introduce you our second speaker, Dr. Manikandan. He is IISc alumni. He did his PhD under Professor Bharadwaj Amrutur. His topic was frequency synthesizer design with low power consumption and low per output levels. So he was also working with the Texas Instrument Kilby Labs, where he worked on the ultra low power IoT circuits. Then he worked on the precision analog circuits as well as the data transfer circuits. So without wasting any more time, I would hand over the responsibility of the presentation to Dr. Manikandan. Let's have a small round of applause for our speaker.
So, thanks for the. So, what we are going to do in the next 1 hour is we are going to take three circuit examples for wideband high PSRR design, fast transient response design, and low quiescent current design. We are going to see 3 LDO designs. If you are given the set of specifications, there is a conventional way of designing these LDO circuits we follow now. We will translate that methods, or we will come up with the GMID or the lookup table based design methods for these 3 topologies. Okay, given a set of specifications, how to design this LDO and without iteration, the first time correct design. Okay, that is the ultimate goal. If you are using square law, you are going to go rounds and rounds of checking the PSRR is meeting or not, the errors are there, it's not meeting. So we are going to show first time correct design by following this lookup table based design methods. So let's start with the wideband high PSRR. When I say wideband high PSRR, the LDO is supposed to support in power supply rejection characteristics in this way. When I say wideband, for a wide range of frequencies, the PSRR number should be as low as possible. So this is the design goal for such an LDO. Okay. So given this, then what do I? If given this is the specification, there are 2 specifications. What is the DC PSRR and what is the PSRR numbers across this frequency range? What is this max and what is this DC? Correct. So if you take a typical wideband high PSRR design, so these are the set of specifications. Now, if you look at the PSRR numbers, there is a DC PSRR target. Let's say less than minus 40 dB DC PSRR target, and say max PSRR of say minus 20. That means it doesn't go to 0 all the way up to 0. It is always less than minus 20 across all frequency ranges. Okay. So these 2 specifications are tied to the wideband high PSRR topology of this LDO. Okay. And other than this, all these specifications come along with the LDO. So what is the V in, what is the V out? V in to V out difference, we call it as dropout, which is 0.4 in this case. Load current, what is the load current range? The load current min, say 2 milliampere, load current max, say 10 milliampere. So when the load current changes from 2 milliampere, 10 milliampere, your operating points are going to change. Your poles and zeros are going to move. You have to find the worst case pole. We have to understand the worst case stability stability conditions, which is 2 milliampere or 10 milliampere. And load capacitance choice. In this case, we are choosing off-chip 1 microfarad cap because our goal is wideband high PSRR. Okay. So these are very typical specs. The CL of 1 microfarad, these 2 PSRR numbers will drive the design of this LDO when you look at the wideband high PSRR design. Okay. So when you say design, what is the ultimate goal? Given this table, reflect all these 2 transistor dimensions, right? Tie all these specifications to transistor dimensions, and once you come up with the transistor dimensions, just put it in your design and see the results. It is matching to this table. Okay, this is the ultimate goal. Given this table, find out all the WLs of these transistors and simulate again to check whether it's meeting this. Correct? Simulate and take. For now, we are stopping to simulate. Okay. So when we follow square law, we have to meet this table. Means we follow square law to come up with our WLs, which will lead to some specifications not met, or we'll go to 3 cycles of iterations to meet this table in the end. Okay, so we are going to avoid that iterations by following lookup table based approach. Okay, so the ultimate goal is to come up with WLs of all these transistors M1 to M8. In this case, M8 is the phosphate. Phosphate has to support V, means V source is V in, V drain is 1. Which is V out, which is 0.4 volt VDS. Okay, in this case, VDS is 0.4 volt, V drop out, and it has to support 2 milliampere to 10 milliampere. Okay, how would you size M8? You would assume some overdrive voltage of 200 millivolt and use square law to come up with W and L, W by L value, right? And this is a power FET, this is a very big device, supports large current. You would have chosen L min and then arrived at the value of W, correct? Now, if you follow the square law, means lookup table approach, we would have we need to come up with the tech plots. In this case, the tech plots is only for L because we already know that the phosphate transistor has to be use minimum length as a dimensions, and we know the VDS is 0.4 volts. Okay, like somebody was mentioning telescopic cascode, which is very low VDS. And in this case, I know the VDS already, so I know the VDS value, I know the length value. Then my tech plot generating this tech plot is only VGS stream. Okay, only one stream. Okay. So now if you do that, then GM-RO versus GM by ID, ID by W versus GM by ID, these are the three tech plots available with me. To size the transistor, which tech plot you would pick in this case? ID by W, right? Given the current, given the load current of say 10 milli, this has to be sized for worst case current, which is 10 milliampere load current. So given the current, I want L is L mean, I want the W of this FET, correct? So given L is L mean, GM by ID I'm picking as 10. So now these are the values of which derived from the lookup tables, which is GM-RO value of this 32.3, whatever, this 8.8, this 5.7. So these are the values from the tech plots. This three lines replaces your square law. Okay, these three lines replaces your square law. Now, given the load current of 10, I know how to get W. W is I load by ID by W, which is say in this case 1.1 millimeter and things like that. And if I know ID means I know GM by ID is 10. If I know ID, I can tell what will be the GM of the phosphate. If I know GM from tech plot, I know the GM or not, so I can tell what is the RO of the FET. If I know the FT, I can tell what is the CGG of the FET. These are the DC operating points of the FET, right? So now you see in this case, we have not used any square law anywhere. You have got all these design parameters, DC operating points, W and W for the FET for a given L-min and load current just by looking at the tech plots. Okay, so this is just this is the phosphate design. This is how the sizing of FET will proceed in this way for given any current. Okay, this is not restricted to only this 10 milliampere current. It can be for 100 microamp current, 2 nanoampere current, anything. Okay. This is okay. You are able to follow this. If you are able to follow this, we are good. Yeah, we'll do good in the sequence. Okay, I know length and width of this right now, MH, right? Now, what next? I will go to the different FETs, which is M4, M5 is the input pair, M6, M7 is the PMOS load, and all these are bias transistors, right? Now I have to arrive at the WLs of the next set. Now, what is the goal? Goal is the DC PSRR. DC PSRR of say minus 40 dB, right? This is the DC PSRR. So we have to size the FET or size the power FET is always sized for 10 maximum load current. The loop gain is sized, loop gain supports the PSRR state. Okay. So the ultimate goal is to have a loop gain, which is PSRR is typically 1 over loop gain. So that sets the target of say 1000. So the loop gain target, which is 1 over PSRR, in this case, if you say 40 dB PSRR state, assume say 20 dB margin and say 60 dB, which is 1000, loop gain of 1000. Okay. So this translates to the DC PSRR state. Okay. So this is the overall loop gain. Okay. If you say loop gain, there are two amplifiers here. This is the diff amp plus this is the second stage amp, right? So what is the second stage amp gain? GM-RO, right? GM-RO is the second stage amp gain. So without running simulations, I can tell you what will be the second stage gain. Now, if I know the second stage gain, what will be the diff amp gain? Diff amp gain is the diff amp gain into the second stage gain is 1000. 1000 divided by 32, whatever this number, this gives you the first stage gain. Now we have to size the diff amp to meet this DC gain. Okay. So this is addressing the PSRR spec, DC PSRR spec. So the other things are this is wideband high PSRR design. That means the worst case is heavy load condition. Okay. So if you see the second pole equation is 1 by RO CL. This is this number. If you translate to in frequency, this is the around 500 hertz, 492 hertz, right? So this is the this is the worst case condition. Means we should not take the light load RO 1 by RO CL, we should take the heavy load 1 by RO CL in this case. Okay. So if I in this case, if I make the UGB equal to this is the dominant pole. Now this is the second non-dominant pole. If I make second dominant pole equal to UGB, I get phase margin of 45 degree. Okay. So omega UGB equal to omega P1, I get 45 degree. What is omega UGB? This is DC gain into first pole. DC gain into first pole. If you treat it as a first order system, DC gain into first pole is the UGB point, right? So DC gain into first pole, this is around means whatever this is 3.1 kiloradians, this is 3100 kiloradians. So my UGB point should be this. Then comes to the third non-dominant pole location. Non-dominant pole location is 1 by 2 pi this RO diff into CGG8. Because why CGG8? Because this is dominant pole. By the time dominant pole comes, this state becomes inactive, right? So then it is only there is no Miller multiplication. The gain of this state becomes less than 1. There is no Miller multiplication. Then the total cap at this point is only CGS plus CGD, which is nothing but CGG8. Okay. So CGG8 also I get from Technology-LUT. So 1 by 2 pi CGG8 I know. I want to find out what is this output impedance. Output impedance from this expression is 170. Okay. This is okay. If this is just the means finding omega P1, omega P2. Now all these things I'm from all these worst cases I'm tying back to what is the output impedance needed for that design. Yes. This one, ROT2, which ROT2 is output impedance at this node. Okay, this is nothing but RO8 parallel RO3. So CL value we know, correct? RO, how to find out RO? RO is RO8. Means RO8 is a small number, which is say around 323 ohms. This will be in kilo ohms or mega ohms. So small resistance in parallel to big resistance will be only the small resistance. No, these are from text plots. From these three values taken from text plots, I know GM, which I have calculated GM here because GM by ID is kept as 10. GM is into current. GM by ID into current. So which is 0.1 Siemens. I know GM. This is from the text plot. So there is no simulations at this point. We are all understanding. We are decoding all the DC operating points just from the text plots shown here. So these are the DC operating points, right? The RO8. So you know the RO8 CL value, you know. Then I can write what is omega. Okay, this is heavy load. Heavy load is worst case condition, and this text plot point is taken for a 10 milliampere current condition. So that's why you can use it here. Okay, so from what do I know? I know this pole frequency. I know the output impedance at this node. Okay. So and the DC gain needed from the DFAM. So this is 31. I know this output resistance calculated as this. Now designing the DFAM input pairs. Okay. So to design DFAM input pairs, I'm assuming some bias current given, which is in this case say 50 microampere bias current, which is splitting as X.
Just had one question. You mentioned that for that CC, the Miller multiplication may not be applicable because the gain is small.
Yes, gain is less than 1.
But the gain that you have calculated is 31, right?
DC gain. There is DC gain. There is DC gain. After the pole has come,
Okay.
at high frequency, there is no gain. Okay, so coming to input pair, see, I have to somehow tie the performance of the MOSFET back to GM or not, ID by W and FP. Okay, if I'm able to tie that, I can easily get the W and L values on the tech plots. Okay. The goal is to do that. So the tail current is given, say assume 50 microampere. So by 2 is the each MOSFET current, which is in this case 25 microamperes. So what is the gain of this differ? This is nothing but GM4 into ROs. which is GM4 into RO5 into RO7. That is ADIF. I know ADIF as 31 in the previous calculation. So this value I know RO5, RO7. I know RO5, RO7 from this pole placing calculation. So I can tell what is the GM needed from this M4 and M5. Okay. So I had we have found this GM4, GM5 means GM4 and 5 because it is matched transistors. I know ID because that is the Poisson current. It is biased with that current. So now GM is this value, ID is this value. You calculate what is the GM by ID I should look at to design this transistor, which is this value divided by this, which is 10.56. It is different from 10. It can be any value. Means if I would have chosen 50 microampere, this would have become 5. If I was given 10 microampere, it would have become 20 or something like that. Okay. So need not the point there is need not be GM by ID is always 10. It can be any other value also depending on what you want to achieve from the circuit. Okay. So in this case, GM by ID is 10.56. Now, okay, to begin, just there is an assumption here because to come up with the dimensions of this, I should know only RO of that particular transistor. Okay. So if I only thing I know is RO5 parallel RO7, means this combination I know, but I don't know individually what is RO5, what is RO7. Okay. So to simplify this problem, I assume RO5 equal to RO7. That is looking down impedance equal to looking up impedance. If I assume that this becomes RO by 2, or the gain becomes 2 times ADIF, means if you find the intrinsic gain of this MOSFET, GM5 RO5, this becomes 2 times ADIF, 2 times 31, which is 62. Okay. So this is the intrinsic gain needed from this MOSFET. This is the GM needed from this MOSFET. Given the current, means current is the bias current given. Okay. So I know the GM by ID. I know the intrinsic gain. So what do I do next? I try to generate this lookup table. Means now this is GMRO versus GM by ID lookup table. ID by W, FT lookup tables. For the MOSFET, I have generated this lookup tables for only one length, L-min only. In this case, because I'm looking at gain requirement of 62, I don't know whether L-min will give that. So what do? I generate for different lengths. In this case, 540 nanometers, 720 nanometers, 900 nanometers. And my GM by ID is fixed as 10.56 in this case. So 10.56, all these values are at 10.56. My gain requirement is 62. So this 540 will give me 61 point this, or to be safe in this given among these three values I will pick 720. Okay. So if you had a tech plot for 600, I will have picked 600 also. This depends on this tells the complexity of generating such a big lookup table, right? In this case, only three lengths are used to generate the lookup table. So what will this lead to? This lead to again operating point errors, which we'll see later. But this may be okay because you're choosing higher gain value, not a lower gain point. Okay. If I would have chosen 540, I would have seen bigger errors. In this case, I choose 75, which is bigger, higher gain point. I would have seen lesser errors. Okay, so what is it then for the MOSFET M4, M5? I typed down means for the given specification of wideband PSRR and this Poisson current, I brought it down to GM5 RO5 specification number. So this is the back calculation done. Given that GM5 RO5 number, from the tech plot I know it is L4, L5 to be 720 nanometer. Okay. Okay, so this is length of the transistor fixed, GM by ID fixed. Okay. So then for this also, GM by ID is fixed. I have length of the transistor is fixed, 720. So ID by W, I can pick 5.79. Okay. And for this is FT, GM by ID is fixed 10.56. Length is fixed to 720. I pick 1.48 gigahertz, 1.49 gigahertz. So this is the square law replacement step. Okay. So we'll slide down the spec all the way down to GMR0 or GM by ID kind of numbers. And from tech plot, you bring down all the DC operating points. Okay. So ID is bias current, which is 25 microampere, ID by W chosen from TechPlot. Now I can tell what is the W needed for the NMOS input pair. RO is GM taken from TechPlot divided by GM5. GM5 is again derived here, which is this is the RO expected from the NMOS. So what you have decoded here is all the DC operating points about this M4, M5. Okay, I know the GM of this M4, M5. I know for a given ID and for this given gain, I have arrived at W and L. If I use this W and L, I'm going to get this RO and this GM in the DC operating point. Okay, this step is okay.
So
Yes.
what was the bandwidth that you were targeting for the PSRR bandwidth?
Means at all frequencies it should be less than 20. At all frequencies.
Even at gigahertz?
Yes. You mean at a very high frequency, they will get parasitic, means you will get the loop gain only not sufficient to
Correct.
do this thing. So if you see this plot, once the loop gain means means we lose the loop gain, it touches the zero line, and then after that this is the parasitic gap division bringing it down. Right? In this case, because we use 1 microfarad gap, we don't allow it to go all the way to 1. This is the UGB point, and after that it is only gap division bringing it down. After this point, there is no amplifier present.
Okay.
So at all frequencies less than 20, this is the this is possible only if you use higher microfarad cap. If you use a very small cap, it will be something like this.
So we will kind of limit it to under 10 megahertz bandwidth.
Okay, so we know we had seen how to get W by L of this. We have seen how to get W by L of M4 and M5. Now the next step, the PMOS load, how to get M6, M7 W by L. So M6, M7 W by L. For this, to get this PMOS dimension, I assume it should be similar to this M8 characteristics. So in this case, I'm not going to calculate new GM by ID. I'm going to use the same GM by ID as a MOSFET. ID is given. This is the bias current by 2, which is 25 microampere. So GM by ID given, ID given. So GM RO also is the intrinsic gain also is kind of known because we have assumed RO5 equal to RO7. In this case, RO5 equal to RO7 lead to this GM RO of 62, right? Or from this, 286. RO of the NMOSFET should be 285 kilo ohm. So RO, this is M6 and some, right? So this should be same or almost similar intrinsic gain expression only as 2 times AB. Okay, so this is 62. So GM by ID known. This is the intrinsic gain needed. So this is the P-MOSFET transistor tech plots. So P-MOSFET transistor tech plot. This is the GM-RO intrinsic gain plotted versus GM by ID. GM by ID is fixed as 10, and for which length I am getting 62. I am going to pick that length. In this case, say this is 540 nanometer. So this, if there are multiple length points available, I would have chosen much more smaller or something. So in this case, so I know length to be 540, means in the previous case it was 720 or something like this. In this case 540. ID by W taken from tech plot, FT taken from tech plot. From this you calculate the width of the P-MOSFET. P-MOSFET is nothing but this is the 25 microampere current divided by 2.18, which is this. GM known, which is the GM by ID known. This is the GM of the P-MOSFET. RO is same as RO5, which is 240 kilo ohm. So if you are going to plug in all these dimensions and do a DC operating point, all these will be given directly as a DC operating point. No iterations. This is like a first time you will get all these DC operating points kind of, because you are generating all this from the spice only and then arriving in the WL of the MOSFETs. Okay, so last set of transistors, M1, M2, M3, which is only the bias transistor. There is no PSRR or there is no performance requirements on them. It is only given the current, tell me what is the W by L. So assume this length same as M4, M5. Need not be like this. It can be L min, it can be anything. depending on what you want. So I assume the length to be same as this M4, M5, GM by ID same as M4, M5. These are the text slot numbers. Given this current, I just want to find out what is the W which will support all these things. That's all. This is just a bias current transistor. There is no performance requirement to it. Okay. Okay. In summary, from all, given the wideband PSRR, given the DC PSRR, we translated to DC gain. From DC gain and pole locations, we use the tech plots to calculate the W, means length and W of all these pairs. M1, these are bias, these are input pairs, this is PMOS load, this is pass through. All these dimensions arrived using the lookup table based methods. Okay. CC, there is no CC because we are not doing Miller competition, it is only dominant pole competition. This is 1 microfarad. So in the next case, we'll see what is the CC place of it. So what did we do? Means given the LDO specifications table, now we have come to a point that given all the transistor dimensions table. Okay. Now next step, if you put all these dimensions and do a DC operating point shape, all you want to see is GM by ID around 10 for the M8 GM by ID will be 10, which is ID is 10 milliampere, GM is 0.1 Siemens, which is not shown here. GM by ID will be 10. But if you see here, this is VGS is 665, VTH is 485. This translated to around VGS minus VTH of 180 millivolt. This tells that see GM by ID is 10 for this MOSFET, but overdrive voltage is 180 millivolt for this MOSFET. There is a mismatch. Now you can see now. So if square law is correct, this number should be 200 millivolts, correct? But because this technology square law is wrong, so you got GM by ID correctly 10, but VGS minus VT of 110 millivolt. We are moving away from VGS minus VT, so I don't care what is my VGS minus VT. All I care is whether GM by ID is 10, all these dimensions are there. For the given dimensions, given load current, I'm getting proper region and GM by ID. That's what I'm interested in. So this is the PMOS load. This is the tail current source. This is 50 microampere, 1:1 current, 15 microampere. All this also again designed with GM by ID around 10.56, right? So this VGS is 620, around say 485, you will get around 150, 160 millivolt overdrive voltage, right? So which is again an error source, which we don't look at. This is okay, this is okay. For NMOS pair also, again, this VDS 400 millivolt, VDS 400 millivolt, with VGS 670. So this VTH is slightly different. So you will get around 180 millivolt overdrive voltage. So this is in saturation, 25, 25, 25, all these are in saturation. Around overdrive voltages of 180 millivolts. If we have used the square law to arrive at W by L from this, it would have been tough to arrive at this DC operating point in the first iteration itself. Okay. Okay, it doesn't stop here. See, all we need to see is the LDO performance table. So this is only DC operating point. This is okay. So what's next? Evaluate the LDO performance metrics, which is the DC gain, pole 1 frequency, pole 2 frequency. Find the stability is matching to what you have designed for. So this is AC analysis of the LDO closed loop. You see, these are all the DC operating points punched out. GM8 is the MOSFET. M8 is a MOSFET transistor, which is 0.1 Siemens for 10 milliampere. This is what we are designed for. We got exactly 0.1 Siemens. ROUT, which is RO8 only, which is 323 ohms. APAS is the GM RO of the FET, which is 32.3. This is the MOSFET or the second stage gain, DC gain. This is the diffam DC gain, GM4, which is we designed for 0.2. If you see the diffam NMOS, the PMOS load, NMOS load. If you see the GM numbers, 0.264 is the one which we designed for. If you look at the DC operating point, which is 0.259, 0.26 becomes 0.259. At first time you get everything on top. ROUT, RO5 parallel RO7, this is 159 kilo ohm. With this we are not designed for. Okay, let's discuss this also. This is 159 kilo ohm. In calculations, this is NMOS input pair. If you see RO4, RO5, this is 285 kilo ohms. Okay, this is 285 versus 159. What would have been the why it was different? I guess. What? That is the assumption. But I have arrived at all the WLs just by looking using the lookup tables, right? So this also will match. The problem, the reason why it did not match is you look at this VDS or this VDS. This is the NMOSFET we are talking about, right? The NMOSFET M5 VDS is 354 millivolts. Okay. In the tech plots, we used VDS 0.4 volts. This answers the telescopic cascode answer question. So if you use 1.8 volt tech plots, it would have been even worse. Okay. So I used only 0.4 volt around tech plots. If I would have generated 0.35 and 0.45 and chosen even more finer L and Ws, this would have matched exactly on top. 159 would have become 240 kilo ohm. Okay, so this error I was okay to keep because this shows there is a VDS difference in tech plot to DC operating point creates an error in your calculation. Okay, just to emphasize this point, we are just left it. Okay. So now this is GM4, this is R out. What is the different gain? GM4 into RO5 parallel. This is 41. So 41 into 32. This is your loop gain. This is around 1000. 62 means this is what we are designed for, right? This all these dimensions were tied to this 1000 gain. Okay. So the dimensions arrived using the lookup table give you in the first iteration itself about 1000 gain. Okay. Next, the pole frequencies. FP2 is the output pole. This is the cap. This is the input pole, internal pole. Output pole calculated to be 490 means this is from the DC operating point. From this table calculation, 492.8 hertz. The assumption at the beginning of all these calculations, FP2, this is 492 hertz. FP2 492 hertz, FP1 492 kilohertz. Because this is 1000 times for phase margin of 45 degree. If you see the results, FP2, FP1, this is 492 hertz right on top. This is instead of 492 kilohertz, this is 315 kilohertz because of this also. 240 becoming 159 will reduce this also. If I use the tech plot of 350 millivolt, make it 240, this also would have been right on top of and calculation. So this is the UGB point. So this is pole 1, this is pole 2. UGB is this. So there is a pole 2 came before UGB. That means phase margin will become less than 45 degree. So you see here, this is 320, 40 degree phase margin. So this is what we had designed. Means all these things we translated to GMRO, ID by W and FT and arrived at W and L. In the first iteration, this is what we see. Means there is no iteration. There is no process of going around cycles. In the first iteration, you get all these numbers very close to what you want. Even with this 180 millivolt, 200 millivolt error was there in this technology. Okay, so this is heavy load thing. We have designed this for light load. Light load is the best case. Heavy load is the worst case phase margin condition. Light load is the best case. Light load, you see this more than 45 degree means around 53 degree phase margin. So which is also matching to our theory intuitions. We have designed all these things for heavy load and we don't care about light load condition. Light load will be always better than this. And this is the PSRR simulation performance. You see this is PSRR versus frequency. The DC PSRR is minus 50 dB whereas minus 40 was the target. When at all frequencies it is less than 20 dB.
When we did our calculation, these two numbers were never came into picture.
This translated to the DC gain. This translated to 1 microfarad cap. If you use smaller cap, this would have increased. This is again to begin. These are the seed in specifications. Okay, so this is the PSRR spec. Say again, this is the V in transients. Means you give some transients to again. Okay, we have matched all our designs. Now we go to the final LDO performance. LDO performance, you have to maintain the Vout constant irrespective of Vout, V in change, I load change, all these things. So this shows that there is a V in change, say 10 millivolt change. What is the Vout change? Vout change is in microvolts, means the loop is working fine. That's all it says. And you will say what is the overshoot, undershoot, and settling time, and all these things from this thing, from these results. This can be tied to the UGB point. Okay, so UGB is around 400 kilohertz. So 1 over 400 into 5, you will get around around this number. Okay. This is load transient, load changing from light load to heavy load. This is 2 milliampere to 10 milliampere change. Your Vout change. This is Vout delta is around. This is the DC delta. It's around 2 millivolts. So 2 millivolt Vout change for 8 milliampere change. This is the delta V by delta I, which is around 0.316 millivolts. This is nothing but R out by loop gain. Which if you do theoretical analysis for an LDO, load transient load. The DC load regulation is the R out divided by loop gain. So R out for our phosphate was 323 ohms divided by 1330. You will get this as the 0.316 load regulation performance. So again, this is the settling time calculation. All these things matching to the hand calculation. This is the summary of wideband high PSRR design. These are the input specifications: V in, V out, load, load current range, load cap, Poisson current. Up to here, this is specifications along with the PSRR numbers. Then this is the simulated number. These are simulated load transients, load regulation, line regulation, PSRR numbers. Means all overshoot, undershoot, and all the things. There is no iterations involved. Just one time. You master the technology, means how to use the lookup table methodology, like how you mastered square law, you master the GMY based lookup table methodology. Then you apply to the circuit, knowing what the circuit wants. Okay, knowing what the circuit wants, you get in one iteration all this performance done. So this is the methodology to be followed. Again, you have to sit with the transistor to do well in this. And you have to sit with the topology to do well in this. Okay. So understand all the circuits, then you tie it back to the lookup table methodology, like how you tie it to the square law methodology. If you have used square law, means this table will take time to come. Now it is in the first iteration it is. And if you have generated the lookup tables for even finer resolution points, all these things, you would have been right on top of what you want. This is okay. You are able to understand all these things.
One question: the tables, the curves that you had generated. So can we use some kind of interpolation function in MATLAB just to get some approximate value?
This was done using interpolation function. I just did 20 points in this plot. This was MATLAB interpolation function only.
Okay.
You don't need to generate microvolts of this plot. It will. It is again computation intensive, right? That defeats the purpose. The plot I did with the interpolation function is 20 points. Means it is just a 30-second simulation time to generate all these three plots. But again, that came with the experience. Yeah. Okay. Fine. Okay, so this is about wideband PSRR design. Now, if you go to the fast and next to LDO topologies, the methodology is going to be same. We are going to change our wish list from the LDO, what we want from the LDO, and then tie our wish list from the LDO to the GMRO ID by W ST of the lookup tables. Come up with W by S and then just verify once whether that meets the specifications. Okay, this is what we are going to do for the next two topology also. This is something new we want. It will be more interesting, but these two are conventional, like op-amp designs with the output pole dominant compensation or Miller compensation kind of things. Output pole dominant because we use CL of 1 microfarad and our out to be its output pole is the dominant pole. In case of fast transient, if you use 1 microfarad cap, what will happen? See, this is in the case of 1 microfarad, where after this I don't have amplifier present in the loop, right? So if you want Vout to be constant even for very high frequency disturbances, if you want very high frequency disturbances, then you want to move this point slightly to the high frequency. Okay. Then I will not use 1 microfarad cap. If I just change the output cap to capless or very small, then this pole becomes moves to high frequency. This you don't have any control. The input pole you don't have control, right? Because this MOSFET is sized for this load current. CG load cap is fixed. Okay. So here you have the freedom to move the load cap. So all you can do is you can remove this cap to see how fast my design can go. Okay, this is all we can do. Fast and center. So all these specs remain same. The DC's PSRR remains same. Only changes the settling time of 6 microseconds, which we observed in the previous design. Now I want to push it down to few nanoseconds. Okay, this is the fast transient response LDO design. For this, I may not be able to use microfarad of load cap. So what do? I use say 200 picofarad, some small number. Even to support the overshoot undershoot, you need to put some cap here. Without this cap, it will be very bad transients. So you need some load cap. So for this designs, I have assumed some 200 picofarad load caps instead of microfarads. And then design for this PSRR of -40. Okay. So again, how do you design for this? Tie this down to loop gain, tie this to pole frequency locations. Then you come up with the WIL of all this LDO transistors. First step, start with M8 sized for 10 milliampere current. There is no constraint other than that. So assume say GM/ID of 10 TechPlots for Lmin VDS 0.4, VDS 5.4, that is the dropout voltage. Okay, this will come exactly right on top when you simulate the results. Okay, so from TechPlot I get all these parameters. This is the load current. Come up with the W of the MOSFET. These are the DC operating points. This step is same for M8 for given any configuration. Okay, second thing, now because we want to support fast transient, the pole worst case conditions and pole zero expressions change, everything happens. So this summarizes the stability parameters. In this case, P2 is the output pole. Omega P2 heavy is this, light is this. In this case, light is the worst case. Light load is the worst case for this type of an LDO. In the previous case, heavy load was the worst case. In this case, light load is the worst case. So you want to find out what is omega P2. This is the value, and to get phase margin of 60 degree, to get phase margin of 45 degree, you would have placed UGP and omega first non-dominant pole on top of each other. In case of 60 degree, you just place it 2 times more inside. Okay. So this is UGP, FP2 light, FUGB, and this is the DC gain direct means matching to the -40 dB target. This is the fast transistor DC gain from TechPlot. From this, you can tell diffamp gain 31. Okay. From NMOS, again TechPlots. If you want to design only M4, M5, GM/ID, in this case, my omega P1 is the dominant pole, so it is not tied to the DC gain. So I assume GM/ID of NMOSFET to be 10, ID given as 25 microampere. This is the gain needed from M4, M5. From TechPlots, I choose 720 for gain of 62. 720 for gain of 62. These values taken from TechPlot, W taken from TechPlot. Okay. So this is free M4, M5 input pair. For PMOS transistor, again GM/ID 10. Why? Because it is same as assumed to be same as M8. This is the gain requirement L ID/W.
Here the gain is actually 75, right?
Yes.
So you are not taking that into calculation going with 62 itself?
you can adjust that. If you don't adjust that, what you will change is what will change. What will change is this 1330 becoming dollar. Means which is okay for you. That's why I did not bother about it. So loop gain stability parameters, NMOS, W and L taken from tech plots. Again, PMOS, W and L same. The procedure is same taken from tech plots. Bias current transistors again same 50 microampere current L this ID by W taken from tech plot W this. So this is again summary. So what changed? What changed from previous design to now is only this pole 0 location change. M4 M5 design strategy changed. Okay. So this is same as previous case. This is different. This is same as previous case. This is same as previous case. CC, you have to find the value of CC to get the phase margin of 60 degrees. So this is the way to find the CC value. So CL given as 200 picofarad. So this is the summary of all the parameters given the specification change. Now, how do we perform in simulations? Simulations again, these are the DC operating points. Only change is this VDS instead of 400 millivolts, 665 is there. That may create some error in the RO of this. This can be fixed by choosing the right tech plot relationship. Same, this again the DC operating point for the MOSFET, diffamp, DC loop gain, pole 1, pole 2 frequencies. Here we want to support fast transient response. When I say fast transient response, the UGB is shifted to very high frequency. UGB here is 14.2 megahertz. In the previous case, it was around 400 kilohertz. 400 kilohertz changing to 14 megahertz. Okay, that means microseconds will become nanoseconds. That's what it is. If this will translate to. This is the heavy load, light load condition. Light load is the worst case. In this case, light load gives you 53-degree phase margin. Heavy load is more than 60-degree phase margin. So all the theory is matching to the simulation. The theoretical concepts is matching to that. Again, the light load or heavy load worst case condition needs to be understood from the theory. In this case, we did that. We designed with this and we matched to them. So this is the PSRR performance. Here you see this is DC PSRR 48 dB. And instead of wideband high PSRR, now you go and touch all the way 0 and then come back. This is the UGB of the loop, means the amplifier. Here you see the settling times. Settling time, transient settling means given B in transient under low load, light load or heavy load, the transient settling times are around 200 nanoseconds. So this is the fast transient settling time design. Okay. So settling times are 200 nanoseconds. The again DC load regulation, line regulation, all tied to loop gain and output resistance and things like that. All this is all okay. This is what we want to see. This is the summary of fast transient response. Given all these things, now instead of DC PSRR and wideband PSRR spec, like in the previous case, in this case, the DC PSRR plus the transient response, two performance metrics. So map transistor GMRO, GM by ID, ID by WFT to this 50 dB and 200 nanosecond spec, like how it is shown. Arrive at all the W by L. In the first iteration, you meet all the even the LDO performance, not just the DC operating point, LDO performance met. The third design, I will go quick, just 5 minutes because the iteration is same thing. Okay. So the third design, the challenge is for both the previous design, we assumed the quiescent current to be 50 microamperes. Okay. This is okay in high power design. For ultra low power design, we need to be around nanoamperes and even picoamperes. Okay. Whether we want to see whether this methodology will work even at such low currents. This is what is the try behind this showing this example. Okay. Even at 200 nanoampere, will my lookup table methodology match exactly to my hand calculations? This is the goal we want to check. So the steps are going to be same. M8 is phosphate sized for 10 milliampere worst case load current. Okay. So tech plots for LMIN, VDS 0.4, GM by ID 10. Get the tech plot parameters, WA, the path. This remains same.
This is the external compensation.
This is external, this is internal still Miller compensation only. Load cap is 200 picofarad. Still Miller compensated. Interesting.
Your previous circuit, what was the total Poisson current?
50, 50, 50, but we treat this as the total Poisson current. This is only for biasing. We can remove it. This is coming from bias circuits. So if you treat for this circuit, this represents the Poisson current of the total circuit representation. So if this is 50 microampere, I assume 50 microampere is the Poisson current. And now I'm trying to design this with 200 nanoampere bias current. This is the change I want to experiment.
Technically, the Poisson current, reporting Poisson current will be sum of all.
80 plus 50. Under no load, what is the current? That is the Poisson current. For whatever example shown, this is 50 plus 50.
In this case, only the default bias current is 200.
200. That means 200 plus 300 plus 200. That's a representation of your Poisson. So what we want to check is with this current, we want to still use the same methodology and arrive at all W by L and see still it is a first iteration based successful design. That's what we want to check. Okay. So this is the MOSFET sizing and DESE operating points. Now to do this dimensions of this define, okay, how to do this? Now I'm not bothered about the stability and all because this becomes very dominant pole. Okay. So going back to the stability analysis discussion. So this is the low Poisson current stability analysis discussion. So this is the pole 1, this is pole 2. Pole 1 is the dominant pole. UGB is nothing but DC gain into first pole, first order system. This is the UGB. UGB doesn't change with the load current or anything. Because this is nanoampere current, these are very small GMs and very high output resistance. This is GM by CGS. GM is very small. Omega P3 comes before even omega P2. And omega P2 is GM8 by CL. GM8 is phosphate parameter. This has nothing to do with the Poisson current. This has nothing to do with the Poisson current. So this doesn't get affected. Omega P3 gets affected because of Poisson current. Well, means if the Poisson current is small, it came from this here to here. Okay. So because this is fixed, the omega UGB is fixed, this is fixed. The phase margin is not going to change. The omega UGB is fixed, first non-dominant pole is fixed, phase margin is not going to change, and this is at such low frequency. This is like a 90-degree phase margin design, like a first order system design. Okay. So that's why for a low Poisson current, for that example, I was not worried about the stability analysis. So then how to strategize, how to come up with you have to tie the performance to something, tie the WLs to something. So how we did this is set the this 4 steps still summarizes the full design strategy. Okay. So typically for low Poisson current designs, you will see W by Ls very small, right? For a given VGS minus VT of 200 millivolt or 180 millivolt, if you are trying to reduce the current, your aspect ratios are going to be very small. Aspect ratios can be less than 1 also. Means W can be less than length also. Okay. So here length I assume to be max length, whatever max length supported by technology. Say 80% of that. I reach to the 80% of that. Okay. Let's say L max is 20 micrometer for a given technology. I go up to 16 micrometer or something like that. Okay. This is just an assumption to begin with. Because I'm saying that W can be less than L, why not push length all the way maximum to the technology limits? This is the thought behind doing this. So L is fixed. Like in a phosphate, L is L min. Now for the DIPAMs, L is L max, right? So then for a single length, you are going to generate tech plots for all these transistors, not for different lengths, for a single length, right? For a single length, you generate tech plots and get the GMRO, ID by W, FT values, all these things. Now, set W also to the minimum possible. Okay, what is minimum? W min is the minimum. I don't want to go to 1 into W min. I just kept 20% above W min. So this is 1.2 into W min. What does this step do? This is W by L fixed to be very low value as possible. That means this will tell what is the lowest current possible for this design to work, right? So what is IQ min now? IQ min is ID by W into this W what we assume, right? So the smaller this number, the smaller IQ min is going to be. This is taken from TechPlot. ID by W is taken from TechPlot. W for use the minimum, so this you get IQ min. These are other than, if you know the IQ min, then these are bias transistors, these are CMOS nodes. This will be just ID by W, ID by W kind of. Okay. So this is the tech plots generated for L equal to 16 micrometer. Means just 1 L tech plots, GMRO values taken for coming up with the size of M4, M5. See, the step assumes calculation of what is the minimum quiescent current. So the minimum quiescent current here is 61 nanoampere. Okay. So assume the L to be L max, W to be W min. From these step plots, calculate what is the quiescent current needed. So this is 61 nanoampere. That means what? This is 61 nanoampere. This is 61 nanoampere. 2 times this is 120 nanoampere. Quiescent current now is 120 nanoampere function. Not 50 microampere. This is 120 nanoampere. So again, we arrayed all these W by Ls based on this tech plots and calculated IQ min also based on this tech plot. What is possible? Okay. So now this is the DC operating points after summarizing everything. Means all the transistors length is L max. Only for MOSFET length is L min. Okay. For this W is calculated using the strategy and tech plots. W calculated using the tech plot. Means all these dimensions now arrived at for a low quiescent current using the Technology-Lookup Table. Now just plug in the values for in this schematic and do DC operating point analysis. You get the similar same overdrive voltage. Means what is the overdrive? GM by ID we designed with the 10, right? Overdrive voltage around say 180 millivolts in the previous cases. You get even for this low quiescent current design the similar numbers. And for 60 nanoampere, 120 nanoampere designs also you meet around overdrive of 180 millivolt and things like that. Okay. So this is the at least the methodology till we arrived used. This works for even nanoampere currents, 120 nanoampere current and 60 nanoampere current. This is what we want to check. Okay. Now, what is the next step? Check all the performance metrics. We said this is a first order system. When it's a first order system, DC gain into first pole. This is the UGB point. Okay, so here it is say 4000 something into this is the first pole. Sorry, this is the first pole. You get this 79 point something like that. So this is like a 20 dB slope, and this is the UGB. So this is like a first order system, and there is this omega P3 and omega P2 comes this thing. So all these things same as your theoretical assumptions. And with respect to heavy current, heavy load or light load, we don't see this gain characteristics, phase characteristics changing. So there is no phase margin change. Okay, it is independent of load current, light load current, heavy load current. This is all again theoretical understanding. This is being validated here. First order response, first order transients. Any transient you give, the settling will be the first order settling response, RC settling response. At 5 tau, you can see the settle to 99% value. Okay, this is load transient. Again, DC is function of output resistance and the loop gain. So in this case, the loop gain is 4000 as against 1000 in the previous designs. Because we did not design for this, all we designed for this low quiescent current. Given a low quiescent current, you get a larger ROT. ROT is mega ohms here, not kilo ohms. RO is 1 over lambda ID or 1 over proportion to 1 over ID. ID is nanoampere, this will be in mega ohms. Gain also will be proportional. So then what will happen? Then your DC regulation also will be very, very small number. And the settling characteristics will be first order settling characteristics. So now this is the summary of this. This design is only total say low nanoampere quiescent current, load reduction, value division. PSR numbers met 50 dB because 60 dB PSR ties to gain of 1,000. Now we are gain of 4,000 and things like that. So this should be easily made. The problem here is the loop bandwidth. Loop bandwidth is the first port is at a very low hertz, and the loop bandwidth is around kilohertz kind of number. So your transient response time will be very high. In this case, it is 10 microsecond transient response. Okay. So LDO designed with this quiescent current using tied back to GMR or IDBW LED methodology. It works fine here as well. This is the comparison of three LDOs which we have looked at today. First one is wideband high PSRR, means at high frequency also it is a very good PSRR. Second one, fast transient response, 200 nanosecond. Third one, low quiescent current design, okay, to 120 nanoampere design. So all given any wish list, given a wish list of say I want this kind of means this performance tuned LDO, square law, it is tough to use square law for all these three, and you will go cycles and cycles. Once you master the methodology, it becomes first time you get all the LDO performance kind of thing. So that's what is being demonstrated here also. It was like that. It means when I was doing it for first time, even I was surprised to see all this thing just coming in the first time. So there is very useful methodology going ahead designing circuits in 130 or 65 or 45 or 28 nanometers. This is very good methodology to have in your arsenal. Okay, so along with square law, once you start doing this, you will be following it this only kind of thing. This is summary. I will not go into this. Sakshi.
Thank you, Professor. This is so insightful. Yeah, thank you. I think Professor demonstrated all the three LDO topologies so well. It's been such a fun ride for both of us, one by one, looking at each LDO. I would just summarize by whatever is on the slide. This one, I think, yes, it's all the three designs summarized. But what I think one takeaway would be, as Javed was mentioning, imagine tech would be very soon, say, given to you. Or say a button press will give you a tech link. That's not the catch. The catch is how do I use it? How do I gain the insights for specific analog circuit blocks? So that is a thing that we hope all of you keep doing and sharing insights. The next slide, yeah. I think, the first part is available online a lot, but I'll summarize. A LUT-based approach retains analog insights and helps you with fundamental limits of the circuits. What Professor showed in the third LDO was our goal was how far can we go with respect to low IQ with a certain GM1 ID until we have to change the topology, or we have to understand what do we do for higher GM1 ID. So that is important. Reduces iterations and helps with streamlined design. Open source IC design friendly. So if I have to pass, it's very hard for saying all the tweaks that I've done. So have to have methodology in place. There's no way now. I remember designing my first LDO and how it takes time, disappointment, square law not working, what all not, but it works in the end. If you don't know how you work, then you cannot tell your friend. The last one is facilitates automation with ease. I would just put a star here and be like, let not automation lose insights. This work, thanks to Professor sharing it so well, LDO design trade-offs, very important. Detailed flows for each one of them has been given. So if you can share, if you can see the slides later also, it will help you design everything step by step. That was the goal. But I would just iterate again. Please remember that would be just like a tool, but all these analog circuits would be different, be using how lookup tables. So that's one thing. Thank you.
Change the slide to something else. You want to change the slide and say something?
No. I think this is good. This is good. Amazing audience and yeah.
Thank you. Any questions? We can.
Yeah, so. So thank you, Professor Manikandan, for your session. It was really insightful as well. So now we'll go to the Q&A session. I'll ask the online audience to please keep posting your questions on the chat, and we'll take them up one by one. First up, we'll go to the offline audience and ask for any questions. So anyone here, please raise your hand.
The question is, at what point does the two-stage amplifier performance break so that you have to move to folded cascade apart for lower Q?
For lower Q.
I hope the question is clear.
Okay, go ahead. So, yeah. Hey, why would you go? Okay, so why would I go to a folded cascade? Is to achieve this, and this together. So this is the breaking point. When you say low IQ, this, if you want to make this 200 kilohertz or even 400 kilohertz or megahertz, that is the point I would want to go to high IQ music or folded cascade be. Means achieve this 4000 with the previous design. Means 50 microampere current, 1000 gain design. This is 120 nanoampere design with 4000 gain. So there is a trade-off. But this is bad in this. That is bad in IQ. Folded cascade will be somewhere in between. Okay, it cannot beat this. But that's a bad thing about the settling time. So you can increase the current slightly. If you increase the current slightly, you will fall. You will make this fall. Making this fall will affect this number, the load regulation number, DC load regulation. So you want, this is tied to DC gain. If you want to get the same gain and transient, maybe slightly higher IQ, I will choose for the
Next question. A more very generic question. I think the way it was presented, LDO design looks like a breeze. Okay. So, I mean, really nice. Question is life really going to be a breeze? What happens when, for example, when you do low noise design, it's like high PSRR, low noise typically goes together. And there, does this approach continue to work? So where I'm going is, today, if you look at industrial class designs, it's typically a hybrid, which means you have bipolar and MOS, again for flicker noise and other reasons. So at some stage, you may start degenerating. Or you actually build a hybrid bipolar MOS for very high-end industrial designs. So I would imagine GM/ID may be still applicable on bipolar. There was nothing intrinsic that said you can't do it on bipolar. But at some stage, we start degenerating, especially for intrinsic component noise. You have to start tweaking this process. That's what I mean.
Yes.
I think both of us, yeah, maybe you go first. I would just like one line and then.
I think if your noise parameter is LDO Vout noise, okay. Vout noise, you want some peak to peak number or RMS number, or even spectrum PSU. So it is all tied to what is the load circuit want, right? So from load circuit, if it is my very high phase, very good phase noise VCO, I'm concerned about the supply lines. So that's the place where I will work on low output noise LDO. Okay. So from phase noise state, I tie to Vout noise state. From Vout noise state, you have to match to GMRO IDW F3. Okay. These three parameters of the MOSFET. Okay. Once you do that, then TechPlot will take over to give you the WLs to get that noise performance. So there is this methodology will change. Like this methodology is now PSRR matching to GMRO and this ID by WFT and then W by L. Now we want V and F square function of GMRO ID by L. There are few words where we started working on. The methodology will change. This is only a sizing methodology. Okay, this is not like a LDO best LDO performance. Given the LDO performance, you know how to come up with WLs of all MOSFETs, and then you get the same numbers at the first iteration. So this is only a methodology. So the mapping portion has to be done by us. From noise to GMRO has to be done by us.
I think I would just add, yes, it looks like a base because yeah, surprisingly becomes base. The second thing is instead of choosing a new topology, because I can't design it, you can know the fundamental limits of a topology by this. That's the virtue of this process. I am consciously moving into a new topology, not because I can't design that. I think that is the only nuance. And as Professor said, this methodology is telling me that, oh, if I give you PSRR, how do I tie into the GMI? If you give noise, how do you tie into mathematics? So that part we have to do, because I don't use effects.
One question from my side, like if the load itself is consuming like 2 milliampere and 10 milliampere, with respect to that, microampere is itself small and the nanoampere itself is small. So does it really make sense to move from microampere to nanoampere when the elephant in the room is that 2 milliampere?
Understood. So this is from the application only. So if you take an IoT sensor node, it is it may be waking up in a very deep duty cycle. When I say duty cycles, it will wake up once in a day, work for 10 minutes, and then be in the sleep mode for the entire day.
Good.
Okay. If it is in the sleep mode, what is the load current? Zero. So it is in 0 ampere load current for entire portion of the day. Just for the 10 milliseconds when it wakes up and sends, the load current is 10 milliampere. Okay. If the sleep mode is few microamps leakage current or something, then this becomes quarterly.
So we'll maybe take one more questions from the offline audience. We passed our time.
Yes.
Yeah, you reduce the current in the last step. You reduce the current so that you out of the W parameter with respect to L. So that W by L was less than 1.
Yes.
So can we reduce the current so as to bring the design into that sub-threshold region? I mean, can the same procedure be followed with the sub-threshold design also? Or
Yes.
there will be some alterations?
Yes, it can be
With
followed.
the lookup table.
Yes, it can be followed. See, in this case, if you go to higher GM by IDs, so if I say GM by ID of 10, it is roughly giving me VGS minus VT of 200 millivolts. Okay, when I say sub-threshold design, it may be equal to VGS equal to VT or VGS slightly greater than VT, like say 10 millivolt or something. In that case, GM by ID will be 30, 40, 50 kind of numbers. So then what do you have to do? You have to create this tech plots, extend this x-axis to very high values so that the GM by ID is 15 mil. This overdrive voltage can be very negligible. It's 10 millivolt or something.
Square law will also follow there because square law only.
No, square law won't follow. When VGS becomes close to VT, so yes, we have the answer. So this is x-axis is VGS minus VT. Okay. So this is what square law, Brown law is what square law predicts. This is what your technology says. Okay. So you see the gap. This is 200 millivolt VGS minus VT. As you go up close to subthreshold design, the gap is very high. You cannot use square law. You can forget about square law after this point.
Thank you, everyone. So now we'll move on to the online questions and just be able to take a few of them. So first question is Technolog method more reliable than square law because the technology node decreases most of the time, and if a particular node is not available in some software?
It is reliable. Yes, tech plot means the methodology remains same. You have to create new tech plots. Means because the methodology depends on what you get, which based on this blue curve. Methodology is derived based on this spice curve. Okay. Your answers also will match to what you put in as an input parameter.
Okay, so next up we have a question. What about the PMOS differential input pair in LDO design? So this was posted towards the initial part of the lecture. So
So instead of NMOS, again, we are tying all the performance metrics to GMRO ID by WFT. Instead of NMOS, you have to work with PMOS text plots and PMOS values. PMOS text plots only.
okay, so the last question of the session. Here VDS and length are fixed for theory calculation and DC operating points. VDS of op-amp were different than our theory calculation goes wrong here also.
No, it will not go wrong. We had shown with different. We are shown with different lengths in our examples. In our examples, we are used always L-wing for the MOSFET, right? So L-wing for the MOSFET, 0.54 for the PMOS source, 0.72 for the NMOS, and we have checked it other combinations also. So if we work with the tech plots generated for these things and then we plug in the WLs, we get the performance figure. So it is robust against changes in length.
Just one more question. All three topologies using 7-pack op-amp are designed. Then I need not look for different topologies of op-amp.
We need to say if your coefficient current, like folded cascode example, if you want to meet a very high DC gain and very high fast transient response, maybe moderate coefficient current, then you look at folded cascode topology. And in this case, we have taken this topology only as an example. This is applicable to all other topologies, even all other circuits. You can design LNAs using this methodology. You can design LC operators using this methodology. So this methodology is coming up with W by L tying to the performance measure.
So that would be all to the online and offline audience. If you have any more burning questions, then I'm sure that you can reach out to both our speakers on their official mail IDs, and I'm sure they will be happy to revert back to you. So with that, we come to the end of this session. It was a really great session. We went past our time, but we had such a wonderful audience who, despite the bad weather, came in and sat through the entire session. So we are really thankful for you to come here. And we are also thankful to the online audience who have stuck around, and we hope to see you around in our next sessions as well. So thank you to our dear speakers. You have been wonderful.